Okay, we are back. It is Calculus 1. We're in Chapter 5. We're looking at Section 5.4, Integration Formulas and Net Change Theorem. And so that's on page 22 and 23. So let's take a look at what that involves. 22, 23, there we are. So integration formulas and net change theorem. Let's see, the net signed area. Previously, we assumed that f is continuous and non-negative above the x-axis on the interval a, b. However, if f is continuous and attains both positive and negative values on the interval, then the net signed area is equal to above the x-axis minus below the x-axis. So remember on the packet before, there was a couple of times we integrated and we came up with a negative answer, and I said, don't worry about that, we'll explain it. Well, here's the explanation. Basically, these areas, if we take a look at the sine curve, f of x equal to the sine of x from 0 to 2 pi, where we have the sine going up and going down like that. So there's pi, there's 2 pi, and all of this area, area 1, and all this area, area 2, end up actually wiping each other out. If I take that, the net signed area for the sine curve from the interval from 0 to 2 pi is equal to 0, because we have a1 plus a2, which is 0. And like, how do we know that? Well, we could do it. We could say that, let's integrate 0 to 2 pi of the sine dx. Now remember, it's the antiderivative, so it's negative cosine of x from 0 to 2 pi. And so we do upper minus lower. And here, let's write this is 1, 0, 0, 1, negative 1, 0, and negative 1, and it's coleslaw. So we want the opposite of the cosine of 2 pi minus the opposite of the cosine of 0. And so what is that going to end up being? Well, the cosine is 1, so we have negative 1 minus, and then negative, it's actually in the same spot, 1. And so negative 1 plus 1 is 0. So you could also look at it in terms of like each individual. Like we could go from 0 to pi and from pi to 2 pi and then subtract them, and it would end up being 0 also. I mean, if we looked at that, if we looked at this just from 0 to pi, it would be the same. So everything, we can just jump down to here. It's negative cosine x from 0 to pi. So then we're working here. So we'd have the opposite of the cosine of pi minus the opposite of the cosine of 0. And so this is cosine is 0. And oh, wait. Nope, I did pi over 2. Sorry. That is negative 1. and then minus negative 1. And so we've got negative 1 is 1, and that's plus 1. So this area from here to here is 2. And then that area from there to there, all we're going to do is swap out this and say from pi to 2 pi. And that's actually the same, just switching the numbers around. And that's also 2. And so 2 minus 2 is 0. So it works out to be the same either way. All right. That's actually negative 2 when we put it in there. When we do the switcheroo and we put that first and that second, you end up with a negative minus 1, and so it's negative 2. So this area is negative 2, this area is positive 2, and when we add them together, we get 0. All right, let's look at the velocity function. So v of t is equal to 3t minus 5 in meters per second. For a particle in motion from 0 to 3, find the net displacement of the particle. Okay. So again, we could look at this picture, 1, 2, 3, 4, 5, up 1, 2, 3, and over 1. And then they wanted us to go from 0 to 3. 1, 2, 3, something like that. So it looks from my very rough sketch, there's going to be a little more below than above. All right, but let's find out. From 0 to 3, 3t minus 5 dt. And so we've got antiderivative t squared. We got the 3 there. We got it divided by 2. That's 5x from 0 to 3. And so upper minus lower. 3 times 3 squared divided by 2 minus 5 times 3 minus 3 times 0 squared divided by 2 minus 5 times 0. So that's going to just be 0. 9, 27 halves minus 15, but let's call it 30 halves, right? 15 over 1 and then times 2, so that's 30 halves. And then we end up with negative 3 halves. So the total displacement of the particle, would that be in meters? It's in meters per second. Yeah, that would be in meters. So negative 3 halves, negative 1.5 meters is the total displacement from 0 to 3. Let's see, the net change theorem, the definite integral of the rate of change of quantity f prime of x gives the total change or net change in the quantity on the interval from a to b. Okay. So let's take a look at an example of that. A chemical flows into a storage tank at a rate of 180 plus 3t liters per minute, where t is the time in minutes, and after 60 minutes it's empty, so 0 to 60 inclusive. Find the amount of chemical that flows into the tank during the first 20 minutes. Okay, so we're going to find how many liters pours into the tank. It's going at a constant rate for 60 minutes. But we want to find out how much happens in 20 minutes. So again, if we were to kind of do a sketch of what's going on, this is 180, and we're going to cut it off at 20. We're going to find that area. So let's do it. So we have chemical flow according to time. So we'll call that the chemical flow rate is 180 plus 3t. And we're going from 0 to 20. Plus 3t dt. And so do the antiderivative, 180t plus, that becomes t squared. The 3 is already there. And now we got to also divide by 2. Guys, divide by whatever the power is. From 0 to 20. So we got 180 times 20 plus 3 times 20 squared over 2. That is upper minus lower. Here, let's see. I'll just write that over here. And lower does end up zeroing out. So we're just focused on the upper. That all goes to 0. And so what do we got? 180 times 20 is 3,600. And then 400, and then half of 400 is 200, and then times 3 is 600. Yeah. So 4,200. And what are we in? Liters per minute. So 4,200 liters. After 20 minutes, you'll have 4,200 liters pumped. Okie dokie. All right. Let's look at page 23. Theorem integration of even and odd functions. All right, let f be integrable. On the closed interval from negative a to a. So those are opposites of each other. Well, then we could just double the area from 0 to. So if, here, let me show you. That's not really that big of a revelation. Especially after we just looked at the sine curves and you saw the symmetry there. But look, if we're going from, for the first line, if it's an even function from negative a to a, f of x dx, we could just say that's the same as 2 times 0 to a, f of x dx. All right. If it's an odd function, then negative a to a, f of x dx, that's going to end up to be 0. So that this, when it's an odd function, you're going to have the same amount above as below, and an even function, it's going to be symmetric about the y, so you can just double it. So here, let me show you what this would look like. So an example of an even function. When you take the negative version of whatever number goes in there, it's the same as the positive version. So if I pop in negative x, it'll kick out x, the same thing. So what would that be? What would be an example of an even function that we've seen a lot of? That would be just a parabola centered at 0, 0. The vertex is at 0, 0. And so if I put in a negative 5, I get the same thing as a positive 5. So if I'm going from negative a to positive a, this area is going to be identical to this area. And in order to be an even function, it's an exact reflection over the y-axis. So this is always going to be true. So that's why you could just say, oh, I could just look from 0 to a and then just double it. That's what's going on there. All right, so on the other one, odd functions, When I put in a negative value, I get out the opposite of the original function, not the same as the original function. And so that is, it's a different kind of symmetry. And it's maybe been a while since I've been thinking about that. It's got symmetry about the origin, meaning rotational symmetry. I mean, I could rotate it 180 degrees and get the same picture. So that's a little harder to get your head around, but it's easy when you look at the integral, because from negative a, this amount from here to here is the exact same as this amount from here to here. It's just below the axis instead of above the axis. That's why with odd functions, it's 0 when you go from there to there. With even functions, you could just go from 0 to a and double it, and it would be the same. All right. So trig identities, even and odd, right, with sines and cosines. So here, just really quick, you could jot this down by the little picture. Trig IDs. An even function. An example of an even function that's trig is the cosine. Cosine curve is an even function because if I take the opposite of x, I get the same as the cosine of x. And then an odd function, that is the sine curve. And we kind of confirm that. When I take the opposite of the angle, I end up with the negative version of the sine. And you could do that with All-Star Trig class if you looked at it. So what does that mean? Remember, they're both positive. So if I'm just looking at sines and cosines, both positive in the first, sine is positive in the second. They're both negative in the third, and cosine is positive in the fourth. And so that's what they're talking about. So if you say, okay, well, look, I took the sine of negative 30. Well, if I looked at the sine of 30, the negative 30 would be in the fourth quadrant. It would be the opposite of whatever that is. All right? Cosine of 30 is the same as, because it's positive in the fourth. So first and fourth. Okie. And again, you could see the symmetry if you graph them also. Like I said, it's easier to see the reflective symmetry than it is the rotational symmetry, but they both have it. All right. Let's press on. We'll do a couple examples. Verify that this is an odd function. And so let's do that. All right. We have f of x is equal to from negative pi over 2 to pi over 2. The sine cubed x cosine x plus x cosine x dx. Okay. We're not going to integrate this. That's a calc 2 thing, but we can verify that it's an odd function by just popping in a negative. So let's look at a negative. So we're not going to integrate. We'll just put in a negative x everywhere where you see an x. We're going to put in a negative x and then see what shakes out. So the sine negative x, and remember that's cubed, cosine of negative x plus sine of negative x cosine of negative x. All right, so basically we replaced everything with a negative x, and let's see what happens. So this becomes, what do we have? Negative sine, negative cosine. So the cosine of negative x is really just cosine of negative sine x is the opposite of sine. So I should have left that all-star trig class there. So negative 1 times negative 1 times negative 1 is still negative. So we have a negative there. And then what happens here? Plus the sine of negative x, that is negative sine x. And the cosine of negative x is cosine x. And so we have basically a negative and a negative. I can factor that out and say it is the opposite of sine cubed x cosine x plus the sine x cosine x. So if we wanted confirmation that it is verified, theorem 5.16, that is an odd function because, or an even function rather. No, an odd function, oh goodness. This is an odd function, and we just verified it. Because we put in f of negative x, and it didn't kick out f of x, it kicked out the opposite of f of x. And again, you have to know that, like, here, let's do our little thing. Let me show you what that looks like with actual numbers so you understand why we flipped this sign to positive and we flipped that sign to negative. We flipped that sign to negative, we flipped that sign to positive. If we use an actual 30 degrees, let's go with 30 degrees. So remember pi over 6 and sine and cosine. We won't do the whole chart this time. We'll just do this part, 1/2 and the square root of 3 over 2. All right. So if we did 30 degrees, if you or pi over 6. So if I look at the sine of pi over 6, that is 1/2. But if I look at the sine of negative pi over 6, that is the same as 330 degrees, but it puts me in the fourth quadrant. That is negative 1/2, all-star trig class. And so the only thing positive down here is cosine. And that's why when we did this was a negative 1, that was a negative sign, and then we, even if you take it times itself 3 times, it's still a negative. A negative times a negative times a negative is a negative. So that's why that stayed negative there. That becomes a positive because look, if I take the cosine of pi over 6, so the cosine of 30 degrees, I get the square root of 3 over 2. But if I take the cosine of negative 30 degrees, I also get the square root of 3 over 2. The cosine is positive in the first and the fourth quadrant. And so it works for other quadrants too. If I would have said negative 150 and positive 150, it still shakes out to be the same. So no matter what you pick, that's how those shake out. So that's how we confirmed that this was an odd function. All right, now let's look at an even function. Verify that it's even. Okay, so this one we can integrate. And show you that it's going to work. So here, f of x is equal to, where are we going from? -2 to 2 of x squared plus 1 dx. All right, so this one we can integrate. Let's rewrite it. -2 to 2 of x to the 4th plus x squared dx. And now let's integrate. So we got x to the 5th over 5, x to the 3rd over 3 from -2 to 2, upper minus lower, and pop in the 2's. So 2 to the 5th over 5 plus 2 to the 3rd over 3 minus -2 to the 5th over 5 plus -2 to the 3rd over 3. And so now, what do we end up with? Let's find out. We've got 32. Is that 32? I think it's 32, or is it 64? Oh, I didn't multiply them out. Okay. Well, first I was supposed to verify that it was actually even. Okay. Anyway. Let's go. Let's finish what I got here. 32 fifths plus, is that 32? 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. Okay. And 8/3. And then minus, and then this is going to be negative 32 fifths minus 8. Let's see, 4 times 30. And so check it out. Look, if I just went from 0 to 2, if I went from 0 to 2, this would have all zeroed out, and I would have just had this. But instead, look at what I have. Then minus, it's going to distribute. So I'm going to have 32 fifths plus 32 fifths plus 8/3 plus 8/3, which is the same as times 2, from 0 to 2. And so 64 fifths plus 16/3, and then I do common denominator, and I have to triple that, man. 3, 12, 1, 18, 19, and 5, 30, 80. And is that 275? Oh, wait, there's supposed to be a 5 there somewhere. Ended up with 16 times 17. Oh no, 12, carry the 1, 18, 19, 182, 15ths, 30, or did I mess that up, 16/3? I don't think so, 64. Oh, I think I did it all right. Okay. 2 fifths plus 1/3. What do I got? Times. Oh, I think I have this right. I think I have my notes wrong. Let's see. That should have been times 3. So that should have been a 6. And that should have been times 5. So that should have been an 11. And then 16 times 11. 76. All right. Yeah. 2 to the 4th. Oh, that should have been 2 squared. Dang it. And 4. That is a 12. And then that is a 17. But 42. And 16. 272. Yeah, no, what I had right here. Oh. My 5s and my 2s. It was sloppy writing. Gotta be careful with that sloppy writing. All right. Anyway, what we confirmed is that that was even. We could also confirm that just algebraically pop in on negative x. So f of negative x is equal to negative x to the 4th plus negative x to the 2nd. And then I do that, and I get x to the 4th plus x squared, which is exactly the same as f of x. So f of negative x is equal to f of x. So we confirmed that it's even, and then we confirmed that it's double. You could just take from 0 to 2 and double it, because this is the same as that. All right. All right. So that is it for 5.4.